Okay, welcome back. We are on the last objective for Unit 3 in Honors Math 3. And we're doing a couple things here. One of them, if you're given roots, write the equation. And we've done that before, so we're doing that again. And finding all the roots for a polynomial function. And we've done that before, so we're doing that again. So there must be something extra that we're doing that we haven't shown you before. Let's take a look at the first problem here. Write the fifth degree polynomial function given roots 3 multiplicity 2, that seems normal, -5, that seems normal, and 2 plus and minus root 11. So that's a bit different. When we were writing the equations, we didn't give you one like that before. Other information, we also have f of 1 equals 80. So that seems fairly normal too. Well, let's go ahead and start here. We've got f of x. They told us the name, so use the name that they told you. F of x equals, now don't forget the coefficient of a is always there. Sometimes it's 1, but many times it's not, so we will need to solve for it. The 3 multiplicity 2, so x minus 3 twice, in other words, x minus 3 quantity squared. We've got x plus 5. Now, the 2 plus and minus root 11, this is the new part of what's going on. So I'm going to go to some scratch paper here for a minute, and I'm going to point out that obviously we know that if something is a root, we can write it in the form of x minus r. But sort of like when we had a fraction, we've talked about how we convert it so that it's not just like x minus 1/2 or something like that. Well, in this case, since we have 2 plus and minus root 11, if I have x minus 2 plus root 11 and x minus 2 minus root 11, math grammar does not allow us to leave it in this form. So we need to construct the quadratic that contains those two roots. Now, one way you could do it, you could actually multiply out this trinomial times this trinomial. I don't recommend it. It does work, but I just don't recommend that you do that. So let's go back to the paper, and I'll show you a method that I think is the best method. Now, there's more than one method to do besides just multiplying it out. And so if you look on YouTube or other things, you might find this other methods. But this method that I found, one of my former students, her name was Cheryl, so I call it the Cheryl method. She came up with this method, and I just thought it was the greatest thing. It's really easy, and it's a good thing. Okay, so if we go off to the side here, and we just say x equals, and set it equal to that conjugate pair of roots. So this works when we have this conjugate pair like this. So x equals 2 plus and minus root 11. Now, effectively, what we're doing is we're going backwards from solving by completing the square. So let's get the plus or minus thing by itself. So I'll bring 2 over. So x minus 2 equals plus or minus root 11. And once you get the plus or minus thing by itself, now you're going to square both sides. If you think back to how when we solve by completing the square, we're just going backwards. Now we have to multiply out the x minus 2 quantity squared, but that's pretty easy. X squared minus 4x plus 4 equals. The other side becomes positive, and root 11 times root 11 is 11. Now, get 0 on one side, so bring the 11 over. So x squared minus 4x, and 4 minus 11 is -7, equals 0. Okay, so this x squared minus 4x, x squared minus 4x minus 7, that contains the two roots, the conjugate pair of roots of 2 plus and minus root 11. Okay, and so what we can do now is we can put that x squared minus 4x minus 7, tack it on, And now the only thing we have left to do is actually to solve for a. And that is similar to what we have done before. F of 1 equals 80, so x equals 1 and y equals 80. We plug those values in. So y is 80, x is 1, so 1 minus 3 is negative 2. Of course, it's squared. 1 plus 5 is 6. And 1 minus 4 minus 7 is negative 10. And so we have 80 equals a times, well, let's see, that's 4 times 6, that's 24 times negative 10, negative 240. So a is 80 over negative 240, which is negative 1/3. And so if we replace the a with that negative 1/3, we get our final equation, f of x equals negative 1/3 times x minus 3 quantity squared times x plus 5 times x squared minus 4x minus 7. Okay, problem number 2. Write the equation for a polynomial function with zeros plus and minus 2, 3/5, and 1 minus 3i. Now, didn't we already talk about in the previous lesson the fact that imaginaries come in pairs? Yes, we did. And so the fact that there's a single imaginary there is sticking out like a sore thumb. So the other part that we need to discuss is the fact that not only do imaginaries come in pairs, they come in conjugate pairs. Okay, so what are conjugates? Conjugates are in the form of a plus b and a minus b. So in other words, the only thing that's changing is the sign right in the middle there between them. So if imaginaries come in conjugate pairs, then if we have 1 minus 3i, then we automatically also have its conjugate partner, which is 1 plus 3i. And so it's just checking to see if you're paying attention and realize what's going on. Okay, so now it didn't specify the degree. It might not. But at this point now we have 1, 2, 3, 4, 5 roots. So this is going to be a 5th degree polynomial. Okay, so if we start to write the equation, it didn't actually give us the name of the function, so you can choose. You can do f of x, p of x, y equals, whichever. I'll just do y. Y equals, there is always a coefficient. Sometimes it's 1. We'll need to solve for it. By the way, notice we left the last one in factored form. That's what you want to do. You don't want to multiply that whole thing out, so you want to leave it in factored form. So y equals a, we've got plus and minus 2. Now you could do x minus 2 and x plus 2. Now that's a conjugate pair, and you could actually even write x squared minus 4 if you really want to. The 3/5, don't leave it as x minus 3/5. If you need to go off to the side and use some scratch paper, you can, but really that's 5x minus 3. Okay, notice that if you set that equal to 0, you would get a root of 3/5. The 1 plus and minus 3i, what are we going to do with that? Well, we're going to use Cheryl's method. So I'm going to go off to the side over here, and we've got x equals 1 plus and minus 3i. And so there's no root this time, but really you want to get the plus and minus thing by itself. You're going backwards from solving by completing the square. So subtract 1, x minus 1 equals plus and minus 3i. Square both sides. Yes, you have to multiply out the x minus 1 quantity squared, so you get x squared minus 2x plus 1 equals... Okay, so I'm squaring the right-hand side. I get positive, and I get 9i squared. Okay, now I is not just some ordinary variable, it is the imaginary unit. So you're supposed to remember that I is the square root of -1, and if you square it, you get -1. So this is really x squared minus 2x plus 1 equals -9. Okay, we get 0 on the one side, so I'm going to add 9 to both sides. So I get x squared minus 2x plus 10 equals 0. So the x squared minus 2x plus 10 contains the two roots, the 1 plus and minus 3i. So that becomes part of our equation. So x squared minus 2x plus 10. Okay, so again, really the only thing that's new here is, well, the fact that they come in conjugate pairs. We knew the imaginaries come in pairs, but they come in conjugate pairs every single time. In case you were noticing the 2 plus and minus root 11, that is a conjugate pair. Quite often you will see that the irrationals do come in conjugate pairs, they just don't have to. Quite often they do. But the imaginaries, they do come in pairs, and they do have to be conjugate pairs. So solving for A, the y-intercept is 144, so of course x is 0, and y will be 144. So plugging those values in, we get 144. And I have A, and I have -2 times 2 times -3 times 10. And solving for A, we have it's positive 120. And so A is 144 over 120. Reduce. Let's see, 12 goes into this one 6, and 12 goes into this one 5 times. So 6/5. So replace the A with 6/5, and we've got our final equation. So y equals 6/5 times x minus 2 times x plus 2 times 5x minus 3 times x squared minus 2x plus 10. Okay, and so now we're moving on to the other part of the notes. Okay, so problem number 3. Now we're back to finding all the roots. If I give you the function, so the polynomial function, which is 2x to the 4th minus 13x to the 3rd plus 68x squared plus 2x minus 204. And oh, by the way, I'm giving you a hint. I'm telling you that 3 plus 5i is one of the roots. Now, we know that there are 4 roots, and we already have one of them. And in fact, since that one is imaginary, and we know imaginaries come in conjugate pairs, we actually know 2 of the roots. So we have 3 plus and minus 5i. We have 2 of the 4 roots. Okay. Now, do we want to do the P over Q kind of thing and try to find the other 2? No, we want to use the 3 plus and minus 5i. Now, there's a couple different ways we could do it. We could do it synthetically, and so I'm going to do that first. It doesn't really matter which one you do first, whether you do the 3 plus 5i or the 3 minus 5i. The first time through is kind of messy. I'll go ahead and just do the 3. I'll do the 3 minus 5i first. So in the box goes 3 minus 5i. Okay. Now, when you're doing one like this, spread it out a little bit more. And of course, double check to make sure you didn't skip any powers of x. So we do have 2, -13, 68, 2, and negative 204. And perhaps instead of just skipping one line, maybe you skip 2 lines. Okay, so it's all set up, it's ready to go. First one comes down, it's a 2, and you're going, oh, this is not a big deal. Okay, but we have to multiply the things in the box times that. So 3 times 2 is 6, and negative 5i times 2 is negative 10i. And then we combine those terms. Now combine the like terms. So I've got negative 13 plus the 6, that's negative 7. And then I've got negative 10i plus no other i's, so minus 10i. And you're going, okay, not a big deal. It's pretty easy so far. Okay, now we're multiplying the stuff in the box times the stuff below the line. And it's a binomial times a binomial, so you got to think of foiling things out. I'm going to distribute the 3. 3 times the negative 7 is negative 21. 3 times the negative 10i is negative 30i. Don't be in a huge rush as you're doing this first time through, because one little mistake can mess it all up. Negative 5i times, I'm distributing the negative 5i now. Negative 5i times negative 7 is positive 35i. And negative 5i times negative 10i is positive 50i squared. Positive 50i squared. Of course, I squared is negative 1, so positive 50i squared is actually negative 50. Okay, combine like terms. So I've got 68 minus 50, that's 18, minus 21, that's negative 3. And negative 30i and positive 35i is plus 5i. Okay, so here it goes. 3 times the negative 3 is negative 9. 3 times 5i is plus 15i. Negative 5i times negative 3 is plus 15i. And negative 5i times positive 5i is negative 25i squared. Negative 25i squared. So that's really positive 25. Combine like terms, so I've got 27 minus 9. 27 minus 9, that's 18. And I've got 30i. Okay, we're going to see this time now if things are good or not, because we know we should get a zero remainder, but don't fake it, because if you're faking it, you've made a mistake, and you're never going to catch where it is. So let's just hope we've been doing a good job. 3 times 18, so 3 times 18, that's, well, 3 times 20 is 60, and take away 3 2s, so 54. 3 times 30i is plus 90i. And right here we're going to see negative 5i times 18 is negative 90i. And that's good news, because see how the i's are going to eliminate each other? So let's keep going though. Negative 5i times positive 30i is negative 150i squared. Negative 150i squared. So that's actually positive 150. So we already mentioned the i's eliminate each other, and 54 and 150 is 204, with the negative 204 is 0. Okay, so we made our way through that one well, and so that's good. Now the first time through it is messy no matter which one we chose. We go through the second time with the conjugate, but it's really the second time through is not bad. If you can make it through the first time, the second time through is actually very nice. So here it goes. 2, and then you have 6 plus 10i. So why was I saying it's nice? Well, the i's are going to eliminate each time if you're doing it correctly. So we've got negative 1. And now we do negative 3 and negative 5i. And the i's eliminate each other. So I have negative 6. Okay, I've got negative 18, and I've got negative 30i. And that's good because we do get a remainder of 0. Okay, So whatever's left, we've gone from fourth degree to third degree to second degree. Whatever's left, we have to be able to finish it, whether it factors or not. Because it might not even factor. I mean, we might be giving you something that that doesn't factor, so the P over Q stuff wouldn't even work. But let's look. We've got 2x squared minus x minus 6, and I'm looking at that, and I'm going, oh, I think I might be able to factor that. So 2x, x, let's see, probably 2 and 3, but 2 should go over there, and 3 right there. How about minus and plus? Okay, that looks good. So the factored form for this polynomial, p of x, well, we got the 2x plus 3, we got the x minus 2, and then, well, we've got the polynomial that would contain the 3 plus and minus 5i. We could get that from Cheryl's method. This is not what we're actually after for this problem. We're after all the roots, okay? And so all the roots for this problem, of course, we've got the conjugate pair of imaginaries, so 3 plus and minus 5i. And then we've got negative 3 halves and also positive 2. Okay. Now, there is another way to do this problem. And so I don't want you to feel like you have to do it synthetically. I mean, synthetic works fine. It's just the first time, the first one through is very messy, and you just have to be careful and not in a huge hurry. The second one through will always turn out to be pretty nice. But there is another way to do it, okay? So the other way to do it is by long division. So we've got the 3 plus and minus 5i, and we can use Cheryl's method to get the quadratic that contains those two roots. So we're going to do that right now. So Cheryl's method, x equals 3 plus or minus 5i. And so x minus 3 equals plus or minus 5i. And square both sides. And so I get x squared minus 6x plus 9 equals positive 25i squared. Of course, 25i squared is really negative 25, so I'd have to add 25 to bring it to the other side. So if I do that, x squared minus 6x plus 25 plus, excuse me, 9 plus 25 is 34. So plus 34 equals 0. So there's the polynomial that contains the roots 3 plus and minus 5i. Now, that contains two roots of this polynomial. So if I divide this polynomial, the second degree polynomial, into p of x, we will get a remainder of 0. But we can't do it by synthetic because synthetic can only divide by x to the first things. Okay, but let's go ahead and do it down here because there's options on this type of problem. So we're dividing by x squared minus 6x plus 34, long division, into p of x. P of x is 2x to the fourth minus 13x to the third plus 68x squared plus 2x minus 204. Nice to have a different color that's obviously a different color as we're doing long division. Okay, what times x squared gives me 2x to the fourth? 2x squared. So I get 2x to the fourth. I get negative 12x cubed, and I get positive 68x squared. And we are subtracting, so I need to distribute a negative. Okay, and the first terms go away, and then I get negative x to the third. My x to the seconds eliminate. You could put 0x to the second if you want. You don't have to. Bring down the next term, plus 2x. Okay, what times x squared gives me negative x to the third? Well, negative x. So negative x times x squared is negative x to the third Negative x times negative 6x is positive 6x squared. Negative x times 34 is negative 34x, and I'm going to subtract, so I'm going to distribute a negative. And the first terms are gone. I've got negative 6x squared plus 36x minus 204. Okay, and what times x squared gives me negative 6x squared? Well, negative 6, of course. Negative 6 times x squared is negative 6x squared. Negative 6 times negative 6x is plus 36x. And negative 6 times 34 is negative. Well, 6 times 30 is 180, and 6 times 4 is 24. 180 and 24 is 204. And if I distribute the negative, we get 0 remainder, which verifies the fact that we did construct the polynomial containing the two roots, 3 plus and minus 5i, correctly. And 2x squared minus x minus 6 contains the final two roots. And so if we were to factor right there, which we know is 2x plus 3 and x minus 2, which gives us our last two roots. And so you can see, you can do it either way. It really does work either way.